Hello, this is Toby Barris for DM Answers. Today I'll do a summary of predictive quality control. I've done several blogs over the last few months, and I just wanted to summarize what has been presented so that there is an overview of this method. First of all, we need to have good metrics to be able to make this process work. The predictive quality control process that I've outlined over the previous months is only as good as the metrics that are used. This kind of goes back to this old adage, garbage in, garbage out. There must be some type of causal relationship between the metric and the outcomes from the process being monitored. For instance, if we have a manufacturing process and we want to measure the quality of the product being or coming out the end of the line, then we need to make sure that whatever metrics we're using to measure quality actually relate to the perception of the customer when that product is received by them. We use statistical process control as a method to separate signal from noise. If you're not really familiar with this concept, I would recommend a book by Donald J. Wheeler called Understanding Variation. It's a very good book. It goes into great detail on how SPC charts can help you to separate signal from noise. The idea being here that we want to use the SPC chart to signal when to perform root cause analysis. In other words, we don't want to be reacting to noise and wasting time and effort to chase after something that is not really a problem. Then we use predictor screening in Statistica for root cause analysis. So we have to acknowledge though that we are using observational data, so we need to be aware of confounding that is going on present in our data. So we look for correlations and remove redundant data. Once you find the strongest predictor, you use additional experimentation to determine the root cause. And so let's just walk through a scenario now. So we have a SPC chart that's been created in Statistica, and we notice that there is a data point that is fallen below the lower control limit. This should signal a root cause analysis. Okay, so I go ahead and do the predictor screening in Statistica Data Miner, and I find out that machine 8 has the largest F statistic. Well, what I did is I just blindly went ahead and did this analysis without considering confounding that might exist in my data. So really what I should have done is go and look at correlations that exist between the variables. And if I use the data health node in Statistica, for the variables I'm looking at are all categorical variables. And so I use Kramer's V to assess the correlations. And this is just a small portion of the window. The window is too big to get on the screen here. But you can see there that anything that is really goes towards 1, it's very blue, those are going to be the correlations that we'd be concerned about. That shows redundancy between those variables, and it's not really informative to include redundant variables in this analysis. Okay, so I removed the redundant variables from the analysis, and anything that's in red here was removed. And then I take that reduced data set and I perform predictor screening on that. And in this case, machine 6 comes up as the most important variable. It has the highest F statistic. It also has the highest R squared. Now, the question still remains, though, is it machine 6 or is it machine 8? Because there's confounding between those two variables. The way that they're nested together and just the way that the product flowed through the system, we're unable to determine if the problem lies in machine 6 or machine 8. So there would need to be additional experimentation done in a controlled environment so that you could determine if it really is machine 6 or machine 8 that's causing the problem. Now, I just offer here a couple of suggestions for those people that are interested in learning more about these kind of methodologies. You'll have to do some additional research on your own. One book that I would recommend is called Statistical Engineering by Steiner and McKay. In there, they talk about swap testing, but the point is that there's going to have to be additional experimentation of some sort that will help you to sort out where the problem is. if there's redundancy in the data. Okay, so let's just, in summary, we can use this methodology to get clues for root cause analysis. We always have to remember, though, this is observational data and that correlation does not mean causation. So if I find a variable that shows up as significant, it's on the importance plot or the spreadsheet that shows importance, it could not necessarily tell me everything I need to know. If I use the methodology I pointed out by using the data health node, that will help us to uncover redundancies in the observational data. Once we have that additional information, we can make recommendations for experiments that can definitively determine the root cause. The limitation is that when redundancy exists in the observational data, you cannot take clues from the importance plot at face value. And so that is the recommended sequence of events. To do the correlation analysis, remove redundant variables, and then do the importance plot. So I hope that you find this useful. If anybody has any comments on this methodology, I'd like to hear back. Be aware that I actually use this in my day-to-day job and have found this to be very informative and helps the people in production to get to the root cause much faster than with the standard methods that they employed before having this method. So again, thank you for listening, and I hope to be back in a couple weeks to have a new topic to share with you.